Okay, this is where we were last time. The idea of nodes. To emphasize again, we're not building a new data structure right now. We're not building like a stack or a queue or anything. We're building something more analogous to the array, the container. Sometimes we call something like an array a container. It's just a place to put something. It's not really, it is a data structure, but it's not really a data structure. It's kind of a building block towards the data structures we cared about, right? Like a stack, a queue, okay? So what we're building right now with this linked structure is like a container. It's something we're going to use to build data structures. And its basic structure is, it's effectively an object that has two fields. Data, its contents, that's like what's in the array at that index. That's what the data would be. And then next is a reference to the subsequent node. In an array, that would be like, well, the next index. But this isn't an array. There is no next index. So we need that reference variable, that next reference variable, to refer to the next node. All right? When we build a node class, we're going to make these objects. It's going to be remarkably simple. It's going to have two fields, data and next. Data will be some arbitrary type, T. It'll be generic. And that'll be a reference to the data we care about. And next is a reference to a node that will contain data and a reference to a node, which will contain data and a reference to a node, that will, et cetera, et cetera. And then the methods for that class are going to be just your accessors, probably a toString, equals, whatever. The standard stuff. But there's not really going to be any functionality there. It's just a container for data, really. But we string them together to create this like larger container of several pieces of information. So here's a visualization of some link structure. Head is a reference variable to a node, but it's not a node, it's just a reference variable. The thing it references, that light blue box, that is the node. What's not shown in this structure are the references to the data. We're ignoring the data for a moment. But what is shown is a reference to its subsequent node. So head is a reference to that blue box. Head's next is the arrow that points to the green box. Head's next is the arrow that points to that teal or whatever color that is. And head's next is the black box. And who can tell me what head's next is? All of them. No, that was a bit of a trick question, I suppose, because there is no arrow at the end. But a reference variable next would exist, it just references nothing. It's the end. So everything has a next, except the last one, which has a next, it's pointing to nothing. Am I recording? Yes. So what's neat about these link structures is, like if I have an array, there's a million things in that array. And I want to say, okay, I have something new, I need to put it index 0. But I don't want to replace anything though. And you're like, well shit, I got to move all 1 million things down one to make room. It's like imagine that row right there, right? If I wanted to put someone in your seat, I'd have to move everyone down to make room. And so that your seat would be empty that someone else could sit in. That's the idea. With a link structure, I don't need to do any of that moving at all. I just need to be clever with how I update my reference variables. So, for example, I want this blue node to be added to the front of this link structure. Right now the order is yellow, gray, black. But what I want it to be is blue, yellow, gray, black. And this is my situation. I have head, which is a reference to the yellow, which happens to be the beginning of some link structure. And then I have node, which is a reference to some new node that I want to insert to the beginning. So how am I going to do that? Well, I will say, okay, node, set your next to head. Now, when I set nodes next to head, what is head? Head is a reference variable to the yellow thing. So when I say node, set your next to head, I'm setting it to the reference, to what it's referencing. So nodes next, this would create an arrow that points to the yellow one. All right? So now, when you look at this link structure, you could say, okay, yeah, so now it's like yellow, or blue, yellow, gray, black. But we're not quite done yet, because I always want to have that reference variable head reference the beginning of my link structure. So what do? Head equals node. Great. I say head equals node, we get this. Sure, node also references the same thing head references. We have aliases. But that's fine here, because what really mattered was head is always going to reference the beginning of my link structure. Remember, head itself is not a node, it's a reference to a node. And each node has a reference to subsequent nodes, unless it's the last, which it does have a reference, it's just null. But that's the situation. How many steps were involved? 2. I suppose it depends on how you count. Do I count creating a new node? Let's assume the new node exists. What do? Set the new nodes next to the head, or to what head references, and then set head to reference the new node, the new beginning of the list, or the link structure. Now, how many steps was that? 2. But how many things were in this list? There were 3, now there are 4. If I had 1 billion things in this list, how many steps would it be? 2. The amount of work is constant. It was 2 steps, regardless of how many things were in my collection. N could be 1 billion, it's still 2 steps. It could be 10 billion, it's 2 steps. I can multiply n by 1 million, still 2 steps. It's constant work. But with the array, if I had an array with 10 things in it and I wanted to add something in the beginning, how much work is it? 10. I have to move all 10 things down. If I double the size to 20, I have to do twice as much work. If there's 1 billion things in there, I have to move 1 billion things before I can put something in the beginning. Now that sounds bad, and at the end of the day, it's a linear time algorithm to make room. The implementation of adding something to the beginning of an array, making room for it first, is linear. Which isn't that bad, but it's linear. But constant time, if you have a way to add something to the beginning of something in constant time, that's way better. Way better. You want a constant time algorithm. You do. Like, that's just the way it is. That's way better. Any questions about that? Yeah.
If you were to add like another node on top of this, would you also have to change the reference of the old node to be the newest one?
I'm not sure what you mean, but let's say there's a purple box I want to add to the front.
Yeah.
I'll call the purple box will be referenced by a variable called some other node. Oh, is what you're asking about the node reference variable? After the new node's added, the node reference variable, I don't give a shit about it anymore. That was only there because I needed to reference the new one I wanted to add. Yeah. So it doesn't need to get updated it doesn't need to continue to be an alias for head. It was just a temporary step. So now let's say I want to add to the middle. Let's say I happen to know I want this blue box to come between the teal. Is that teal? I think I asked this last time. Is it cyan? Cyan's more like light blue.
Yeah, cyan is not really any green to it.
Okay, so we'll call that teal then, right? Aqua? It's the green-blue one, right? I want to add it between the green-blue one and the black one. How do I do it? Take a moment. I'm going to give you 2 minutes. This is the situation I have. I want you to take a few minutes, think, talk amongst yourselves, and come up with the series of steps you have to take to insert it such that the order is light blue, green, yellow. What colors did I pick here? Green, yellow, green, blue, blue, black. Okay? I want it to go this one, this one, this one, this one, this one. Take a few moments. I'll give you 2 minutes to think, talk about it, come up with the steps. Half of you will be right, half of you will be wrong. But all of you have the potential to be correct.
And then just do the same operation using just like the new node temporary next. And then the next temporary variable to the new node.
Does anyone in here have whiteboard markers on them by chance? You have the Sharpie? I don't think those work on here, do they? I usually have them, but I lost them a couple months back. I'm gonna grab a few. Don't let me forget to give them back to you though. Look at you. You came well prepared. Oh, beautiful too, right? Look at this.
Yeah, well, you have to have the temporary variable. Unless you want to say, next. No, next. Temporary variable, there's a reference variable to traverse the list.
So, first thing we're probably going to want is what I heard you talking about. We don't need this. We're probably going to want it though. Is we're going to need another reference variable to reference the node before the insertion point. So, following this, we'll have it here. Can you see this pretty well at the back? Good stuff. All right? I would start with current here, and I would say, do I want to add it after this one? No. After this one? No. After this one? Yes. Okay, we found it. So we do have to do some like linear search first to find where it goes. But once we find where it goes, what do we do? Who wants to, what's the first step?
Set the new nodes next to the currents next.
Set the new nodes next to be the currents next. So currents next is this one. New nodes next you want to go to here. Is that correct? Now what?
Set currents next to the new node.
Set currents next, which is this, to actually not be this, but to be this. Is that correct? That's what you mean? Who here agrees? Makes sense. Yeah. Very good. Now, how many steps were involved?
1, 2, 3, and then a 2.
So, this one's kind of tricky, because once we had a reference to this one, once we had access to the node, it was update this, like 2 steps. But we still did need to find where it needs to go. Right? And what's interesting here, if you compare this to an array, you might say, well, just like an array, if I needed to do a search first to find where something gets inserted, I still have to do a linear search in order n, the linear time algorithm, right? But what's a little different here is, even if I said, you don't need to do a linear search, you don't need to find where to insert it. I want you to insert it such that this becomes the fourth thing. We still need to move.
Things after that.
We still need to move this. We still need to get this to reference the correct before one, which is still going to be, well, how, like, I still need to go down. And the amount of steps it's going to take to go down is going to depend on, well, how far down do I have to go? How many times do I have to say current equals currents dot next? Current equals currents next. Current equals currents next, and so on. So no matter what, with an array, if I said add this after the fourth one, boom. I jump right to the fourth one and I, make room for it, add it. Making room for it is linear time work with an array. And then I can insert it. But the linear work for the link structure is the other way. The linear work is being able to access the thing before. Inserting it is the two steps. I don't need to make room. Nothing needs to move down an array. I just insert it like that, 2 steps. But I still need to say, okay, current equals head. Current equals currents next. Current equals currents next. And so on, right? For those of you wondering about current equals currents next, imagine current was this. What's currents next? Well, that's this node. So current, the reference variable current, reference currents next. Well, that's just that. Current equals currents next. Well, currents next is this one. Set current reference its next. Well, right there. That's your typical way of iterating down a link structure. Yes?
So there's like no indexing for
You can't index a link structure directly. That's my point. So, with an array, to look up the nth thing in an array, it's a constant time lookup. You just say, give me the array at index n. With a link structure, all I ever have is a reference to the head. If I say, give me the nth thing, you go, all right. Current, set a counter to n, current equals current, it's next. Next. You got to move all the way, you have to iterate down to find it. With an array, it's constant time lookup. But with the array, to do the insertion, we still have to move things down. Now finally, the last thing I do for inserting into an, actually no. Let me show you one last thing here. You may remember I made a comment about half of you will be wrong. And it comes down to one little funny case. The way you would be wrong, so remember the order you said was set the new nodes next to currents next. Then currents next is the new node. But let's say we were to do that in the other order. Let's say I were to say, okay, current, set your next to the new node. All right, great. That means this reference disappears. And then what do?
No reference to that.
We're screwed. I'm really far away from the mic. Hopefully it's picking me up. But we're screwed. Because you would say, well, set the new nodes next to that one. And I go, how? And you say, well, just do it. And I go, but how? I don't have a reference variable to that thing. I can't access that anymore. What would happen to that node? Garbage collection. Imagine this node was followed by 1 billion things that were super important. It's gone. It's good as gone. The computer goes, oh, they don't care about it anymore. See ya. That's what would happen. So you got to be careful the order that you do it. Now finally, inserting at the end. Now let's just say this particular example. What's kind of interesting about inserting at the end is it's actually exactly the same as inserting in the middle. The algorithm is identical. Because the last node has a next. I'll just represent null as this dot. So what was the algorithm? Set the new nodes next to be the current nodes next. Currents next is the new node. But in this case, it loses out to the array. Because the array, it's constant time to add to the end of an array. Unless you have to expand capacity, which is kind of a one-off. But with the link structure, we still have to go all the way down. The only way, just one second, the only way it wouldn't lose to the array, and some people do this, is if in your link structure, you always kept track of two references. The head and the tail. If you have a reference variable to always the last thing, inserting at the end is trivial, right? Tails next is the new node, tail equals tails next. That's how I would do it. Maybe I said that too fast. Right? Imagine this was the situation. Tail, your next is going to be this new node. And now we need to update the tail reference variable such that it actually is referencing the tail. Well, tails next is this new node. So tail equals tails next, so just update the reference variable to be its successor. And there we go. You had a comment?
Yeah, that was
Just about that reference? Yeah. So this might make sense to include if you knew you're going to be adding to the end a lot or something. You'll notice that there's a phrase you've probably heard, or maybe you haven't, but there's a common phrase in programming or engineering in general, is there's no free lunch. You win some, you lose some. Arrays are better here, but worse here. Link structures are better here, but worse here. You win some, you lose some. There's no free lunch. All right? Every once in a while, there is a free lunch. But when it comes to like engineering, like this type of stuff, it's always a trade-off. There's always a bit of a trade-off. You ever see those things with those triangles? It's got to be good, cheap, and quick. Pick two. Right? There's always a trade-off. Any other questions about that? Okay, that was inserting. The next is removing. Well, removing from the front of a link structure is probably the easiest of all possible things we could do with the link structure. Just add one more node because it looks silly with only 3. Removing from the front is like one step. Head, what's your next? Well, that's this. So head equal head's next. Now you got to remember, if you're ever confused, well, like hold on, you're updating head at the same time. The right-hand side of any like assignment is always done first. So when I say head equals head dot next, head's next, I get a reference to head's next, which is my finger right here. And then I say, okay, head, you're going to be equal to this, what this is referencing. And that would go to here. Right? Now, currently, and listen to the question I'm asking. Currently, what's referencing this node? Nothing. So what happens? It disappears. It doesn't matter. I have no way to access this. If you think to yourself, well, but that references this, you're right, but I can't go backwards. Meaning, this is as good as gone. Right? So this will remove it. It's gone. So removing from the front is probably the easiest. How many steps was that? Pardon? 1. Did you say n? Oh. 1. If this was an array, sure, removing the thing at the beginning is 1 step. But if we want to get rid of that gap, the fact that index 0 is now empty, we have to move everything down 1. So removing from the front with a link structure is constant time. Removing from the front of an array, if we want to eliminate any gaps, is linear time. Trade-off. One's better in this case. Removing from the middle, here's how we typically do it. We'll have two reference variables. Oh, that's funny. It looks like the green one's missing its border. Huh. We'll have two reference variables. You could do it with one. All that really matters. But let's have current be the node I want to eliminate. And previous will be the reference variable to some node before the node I want to remove. And the way I would do it is I would say, okay, previous next is current's next. Done. Very similar to remove from the front. It's just, head is just a reference variable. Previous is a reference to a node that has a reference variable to a successor, the next. Same idea though. So what now references this? Well, we've got a reference variable current, but if it's not really used and that disappears, it disappears. It doesn't matter. We can do this without two reference variables. All I really need is previous. I don't need current. The way I would do it with only just previous, if I would say previous next is previous next next. Previous next next would be the one there. So that's how I do it. And then removing from the end is going to be very similar as well. So, any questions about this adding and removing from the beginning, middle, end stuff? If you're looking at this, you're like, oh, it's simple. Okay, but in practice, students, if I put this on a test, students mess it up a lot. This is an important thing to know. And I feel like the way the course was designed is it might de-emphasize the importance of this. And you might get too focused on the stacks and queues and bags and trees that we build. But the underlying things we're doing in the data structures are important. And this is a big thing, okay? I think next week's lab is all about this, so. Yeah. Everyone's happy with this? No questions, no nothing? Yes?
Maybe I'm not understanding something correctly, but you had your previous last node reference null, that remove the last.
Yep. Which is kind of like, imagine it's this situation. This is current. This is previous. Right? It's going to be the same as remove from the middle. It just so happens that current is also referenced to null.
Okay.
Oh wait. No, I've got it backwards. Well, I've got it back. Not backwards. I've got it off by one. My apologies. Previous, current. There. Right? So current is the one I want to remove, which is actually the last one. Its next is null. So previous next is current's next. Well, that's that. Or previous next is previous next's next. They're the same thing. They're aliases for one another. So how do we actually implement this node class? All right, so, well, remember, reference variables contain a reference to an object and not an object themselves. I've been saying this a lot, but I want to make sure you get it. Head is not a node. Head reference is a node. Very different. So if we want to build this thing, well, we need a field in a class to keep track of the data, which we were ignoring when talking about the adding and removing. All we were showing with the adding and removing with each node is next. We just kind of ignored the data. But of course, that's actually what we're caring about. That's what we're storing. So the data will be there. And we need a field to keep track of each node's next or successor, whatever you want to call it. We need constructors and we need getters and setters. Nodes, the way we're going to implement them, are going to be mutable. We are going to be able to mutate the contents. change the values of the data and next inside each node. That means we have getters and setters. These are called, more generally, they're called accessors and mutators. But often they're called getters and setters. We could implement this such that the nodes are immutable, and maybe we should. There's an argument to say that maybe we should do it that way, but whatever. So, new class, public class node. It's generic T. And the reason we want it to be generic is, well, what's the type of the data we're going to store in the node? I don't care. I want to be able to store any arbitrary object. So we make it generic. And then we have, so the type T for the data, and then next is going to be a reference to a node of type T. It's actually important to include this here. It's a reference to some other generic node. The type of the reference variable is a reference to a generic node. People will make, now I didn't do it this way. There's also an argument, because node is such a simple class, and most programmers are very aware of like, okay, the node class is for these link structures. Because of that, it's not unheard of to see people implement this by making the fields public. Just make them public, give everyone direct access. It doesn't really matter outside of what we're using it for. We could do it that way. I don't like it that way because it kind of starts to break some rules of like how we're supposed to be programming these things, which can create issues later on down the line. So that's why I made them private. We're going to have accessors and mutators. But if you come across an implementation where the nodes fields are public and there's no getters and setters, that's not unheard of. We have two constructors, a default, and then a constructor that takes some data that will automatically store the data. What's up?
Oh, just so when you like actually make a node object, you would have to use a wrapper class as like the type, right? And if you were to just make a node of like the first constructor, it would be its data would be null.
Its data would be null, but the reference variable type would be a reference variable of the type that you specified upon creation.
Yeah, I know that, but like, you know, like for like the primitive like type int,
Yeah.
it can't be null, but an integer is a wrapper class is an object. Or
It's not a wrapper class, but I know what you mean. So it's like the object version. Because it's generic, everything would have to be an object that you had for the generic. You
but
couldn't.
It still can be, but an integer can be null though, right?
Yes, but int can't. Yeah, there we go. You could say, why don't you add another constructor where you give it the second attribute or second parameter to specify what its next would be? Yeah, we could, whatever. I could also have not included this. I just chose to have these two constructors. At this point, we're experienced enough that it's like, well, I've got the two constructors. I could have just had the null one where everything's set to null. But I did it this way because it's not wrong, it's not more right, it's just, this is the way I implemented it. Get data, set data. You know, it's always a bit of a sign that if you ever write a method or a function that's return type, like the type of that function is void, it's a pretty damn good indication that that method or function has a side effect. And we like to avoid side effects. But we are making nodes mutable. It has a side effect. Remember, when I say side effect is a pure function or method, it's something that takes input and gives output, right? This function doesn't have any output, but it changes the state of something. It changes what the data is, right? What the data reference variable references. There's a side effect. Get next returns a node of type T, and then set next to update what it references. So whenever you see like a getter and a setter for all of the fields in the class, There will be people that make an argument to say, just make them public. It doesn't matter, just make them public variables. It doesn't matter. And yeah, that's a fine argument. I still won't do it, but there. Any questions about this node class? It's not particularly interesting. It's basically like a structure that just has two pieces of information. The data and where to find the next node. That's all it is. And an ability to access and update those fields. That's all it is. If you're expecting it to do more, I got bad news. It doesn't. Of course, it's how you use these things in aggregate where you get interesting behavior. I'm just talking about this is how you make a single node. But all of these drawing examples I have is a series of nodes strung together. Yeah, it's when we start to string these nodes together, we get interesting stuff going on. Any questions? So, for example, I'm not going to run this, but here's an example of making a node that's going to, where the data, the type of the data that I want to store is going to be integers. Integers because, as you were saying, we can't put primitive types for generics, they have to be the objects, and so we say integer. So we're making a node reference variable where the type of the data is going to be integer. And the reference variable's name is just head. Head is a common name for the beginning of any link structure. Sometimes it'll be like front first, head, very typical. And it's going to be a new node. So this is starting with a new node and its data is going to be 0. If you're looking at this and you're saying, why don't I need to specify the type here again? Pardon? Yeah, because of that reference variable. This can get weird when you have inheritance going on, but it doesn't matter. This is what they call the diamond operator, which basically means you leave the type blank and it goes like, well, okay, they want integers because the reference variable is there. If you specified integer on the right-hand side, where node integer 0, it worked just fine. So then I make a new node reference variable current node, which references the same thing head references. And then I have another one called new node. So at this point in time, how many reference variables to nodes do I have up until like line 10? How many reference variables for nodes do I have? 3. How many nodes do I actually have? 1. Remember, this doesn't make a copy. Let me draw it. When in doubt, we'll draw. So what do we have? We have head, I'm just going to have as an H, and it's a reference to a node containing, now, as of now it contains a reference to null as the next, and it contains a reference variable to some data, which is the integer 0, right? For simplicity, I'm just going to draw the 0 inside here, even though really it's a reference variable to a 0 somewhere else in memory. But just for simplicity, I'm going to draw it inside the node. But be aware that that's not quite as accurate as it could be drawn. We just get too hairy otherwise. Right, so that's what I have after line 5. I can't tell. 4. From this angle, it's hard to see. And then I have another reference variable called current node, which references the same thing head references. And then I have another reference variable called new node, and which references null. That's what I have at that point in time, at line 10. Any questions about that? So what am I doing? I have a for loop that starts at 1 and goes to, but excludes 10. And I say, the first thing I do is I say, okay, new node, you'll be an actual node. I'm going to draw it sequentially, even though there's no actual, from this code, there's no consequence that there should be anything sequential inside of the computer. How? Let's do it not sequentially for fun. So we've got the reference variable new node, that now references some other node over here that has the value 1 in it, right? That's what happened on line 12. On line 13, we say current node, set your next to reference the new node. All right. There. Then I say, okay, current node equals current node get next. Well, current node, what's your next? Oh, well, that's just this one. And so current node, you're actually just going to reference that. Oops again. This time I is 2. New node, you're going to reference another new node that's over here this time. To be clear, the reason I'm going all over the place, there's no reason to believe that these nodes are in sequence in memory anywhere on your computer. They're just everywhere. And they have a series of references that are just spaghettied throughout RAM. Okay? So that has 2. Current node next is going to be equal to current, or is going to be equal to, okay, what do I say? Current node set your next to the new node. So current node, your next is going to be the new node. And now current node, you're going to be equal to current node's next, which is always the alias for new node. And so on and so on and so on. And then finally down here, we just set current node equal to head. Well, current node is not null. Print out, get the data from the current node equals current node got next. This right here is your common pattern for iterating over a linked collection. Well, something is not null. Do this. And instead of incrementing some counter, the last thing is always current node equals current node's next. Just move it down one. That's your typical structure of a loop for iterating over a linked structure. Any questions about this? So in this example, we had 3 reference variables. One is always to reference the head. We always want to make sure we have a reference to the head of our linked structure. So that, we created it, created the node at the beginning, and then we left head alone. Then we used the 2 other reference variables. The current node was always a reference to like the last node. And then the new node was always a reference to, well, the new node we're creating and adding to the end. So these 2 reference variables were kind of like moving down the line as it was being built. And then when it came to iterating over the link structure, we just had to have current node start at the head and then move down. We never want to change head unless we are actually updating what head references by like inserting to the front or removing from the front of a link structure. But head is usually left alone because it's just the beginning of the link structure. Any questions? Now, head is not a node. This warning is very important. Head is a reference to a node. Head equals some node and head.set next to some node mean 2 entirely different things. This is the result. Imagine head reference this and some node reference this. Saying head equals new node does that. It updates what head references. Saying head dot set next to new node does that. 2 very different things. One updates the reference variable, one instructs the node to do something. Update its next. Cool? And of course, we could have a variation where you have a node that has 2 reference variables, a predecessor and a successor, a previous and next. You could do that, but that gets complicated. Anyways, any last questions? Awesome, thank you. Have a great weekend.